SwayamPrabha. Digital India. Educated India.
Welcome back. In this video we will revisit polymer structures so that we can add on few additional topics and explain the polymer behavior even better. So we will first start with the length of the polymer. We will see the ways how to discuss about the length of a polymer and how it affects the mechanical properties. We will also look at the packing, whether it goes to a crystalline or amorphous and how it affects the mechanical properties. And lastly we will see this concept of tacticity. We will explain about it and see how it affects the mechanical properties as well as the packing. So let us start with the length of the polymer. The way to describe length of a polymer is through this term called the degree of polymerization. First let us see what it means. So it means the total number of monomers in a molecule. So polymers, as we know, is an addition of monomers. So if we have two or more monomers, we should be calling them as a polymer. But the question is, in industrial polymers, what is the typical value of this degree of polymerization? It turns out it is about 1000 to 100,000. So these are the average values. Probably there are some specific polymers which are slightly less or large, but most of the polymers fall in this range. So now let us see how do we discuss the molecular weight of a polymer. So usually it is given as degree of polymerization times molecular weight of a monomer. So let us see this with an example. For example, if you are considering polyethylene where it is C2H4 N, where N is the number of monomers. So dP times the molecular weight of monomer. What is the molecular weight of ethylene monomer? It is carbon 2 times 12 plus 4 it will be 28. So it is dP times 28 will give you the molecular weight of polymer. Let us say for example this dP is around 1000. So the molecular weight of this polyethylene with a degree of polymerization of 1000 will be 28,000. Okay. But the question is, when we prepare a polymer, do we get all molecular chains of the same length? The answer is no. What we usually get is a range of degree of polymerizations, which means the length of the chains vary in the same polymer itself. This figure depicts the variation. On the x axis we have the degree of polymerization and the y axis we have the probability of having chains of, let us say, a dP value around here, and this gives the probability of chains having a dP value of so and so value. So as you can see, there is a large range. So probably these are the locations where it has a small molecular chain, and these are the locations where it has a relatively large molecular chains, but the majority of the molecular chains are somewhere here. So how do we describe this? We describe this using a bar on dP, meaning the average degree of polymerization. So this average degree of polymerization is important to know for a polymer we are using or preparing, because that gives an indication about how the polymer behaves. That we will see in the next slide. So we already mentioned that we should be calling anything a polymer when it has two or more monomers. But the question to be asked is, how many monomers do we need for the polymer to behave as a solid, or to behave as a solid with useful mechanical properties, because that is more important if you are looking from an engineering polymers perspective, right. So let us see that. So typically we are interested in these high polymers. What are high polymers? These are polymers with the average degree of polymerization of 500 or more. So the reason why we look at these high polymers is because then we get solids which have useful mechanical properties. So why does this happen? Because let us say if the polymer lengths are very small, usually what happens is they slide against each other, or with a very small force the secondary bonds which are holding these small molecules, they slide against each other, and then they do not have this solid like behavior, or the mechanical properties are weak. But let us see what influences this dP. Of course, this is dependent on the chemical structure of the polymers or the monomers we choose, but in addition to that it also depends on the way this polymer is processed, or how does the curing or the polymerization takes place. Some of the parameters like at what temperatures these are done, or at what cooling rates we take it from a molten state to a solid state, and other parameters like the kind of additives used or the catalyst used, all of these play a role in arriving at the average degree of polymerization. So, as we said, this affects the mechanical properties. Primary of those are the tensile strength. It also affects the softening temperature, the temperature at which the polymer acts very softer compared to the regular polymer which are usually hard. And then it also affects the viscosity. Viscosity is the resistance to flow. So, maybe when it is in a molten state, we expect that when it is fluid, the resistance to flow is less, but as you cool down, or is it if it polymerizes more and more, the resistance to flow is high, which means the viscosity increases. But here what we are saying is, if the average chain lengths are high, that resistance to deformation or the resistance to flow is high. So, let us look in detail about the tensile strength. How does it vary with degree of polymerization? Usually it is in this order. So, you will notice that the way I have drawn this picture, I did not start from the origin. Instead, we started from somewhere here. This more or less is about 300 dP. So, which means if the degree of polymerization is less than 300, the strength of the polymer is negligible, or it has very less strength. But when the average polymer length or the dP is more than 300, that is when we see some respectable or decent strength in the polymer. So, as you can see, as you increase the degree of polymerization, the tensile strength or the load it can bear before failure increases. Now, let us move into another topic which we have already discussed in a previous video very briefly, but now we will go into more details about how these molecular chains pack together. So, here what we see is a single polymer chain. Single polymer chain, as we know, has a backbone of carbon atoms which gives the strength to the polymers. But we also have looked at saying that between these carbon atoms there is a revolution joint, because of which the polymer chain twists, tangles, like this is a tangle what we say, and it is taking a very arbitrary shape. Now, if we look at the total length of the polymer, I could say the length of the polymer is written in n, let us say, is number of monomers, and lambda, let us say, is length of each monomer, meaning from here to here we will say that this length is defined as this lambda, which is the length of the monomer. So, the total length of the polymer chain, we could have written it as n lambda, right, because it is the number of monomers times the length of the each monomer. But now, if I ask a question, what is the distance between the both ends of the polymer chain? So, which means like from this terminator to this terminator, the distance we write is this, right. And if we have to give a value to what is the distance between the two ends of the polymer, you cannot again use this n times lambda, because this is not like a straight polymer chain. So, it is taking an arbitrary shape. So, usually this is given in terms of n square root of lambda. So, this is an average value between the start and the end of the polymer chain. So, we have discussed about this single polymer chain, but now let us look at how if there are multiple polymer chains, which happens usually when we prepare polymers, how they pack together. So, usually some or few polymers form this crystalline, not all polymers, but few polymers form a crystalline structure. What it means is, as you can see here, these polymer chains fold. The reason why they fold against each other is because these hydrogen atoms, when they come close to each other, there are these interatomic forces like the van der Waals forces or the hydrogen bonds which form, and then when they come close, that secondary bond holds them together. So, in this way they are packed very neatly or closely. Of course, I think I have already mentioned earlier, one should not be confused with the crystallinity of metals where it is very perfect. Here we should take it with a pinch of salt, saying that this is a imperfect crystalline, meaning that there is some order but not a perfect order. So, this I think last time we have shown there is an analogy for you to picturize what we meant by crystallinity is by looking at a continuous printing sheet. So, in olden days when we had these computer printers, there is a continuous sheet which is folded very perfectly, in the sense like because of these folds it fitted into a compact box. But of course, if you open up, it would have taken a much larger space. That is what we meant by amorphous state. So, the other extreme to the one extreme is the crystalline state and the other is the amorphous state. In the amorphous state, it takes a very random structure. So, which means there is no order to the structure. And just to give you an analogy of what we mean by no order, it is something close to spaghetti, meaning like each of these strands are very arbitrarily packed together. We also call this amorphous state as glassy state, because glass again is an amorphous material, meaning there is no order into the way the molecules are arranged. So, these are two extremes, but polymers wise, some of it are amorphous polymers, which means there is no structure into or there is no order into their packing, but some of them are partially crystalline. None of them are completely crystalline because that only happens in metals, but in polymers some of them are we call it either partially crystalline or semi crystalline, because we have some regions like these which are crystalline, but again there are some regions like for example here where things are amorphous. So, between these crystalline blocks we have amorphous regions, therefore, we call it as partially crystalline, meaning there is both crystalline and amorphous polymers. So, in the coming slides what we will see is, in addition to the chemical structure, there are other details or other aspects of the polymer which decides whether the polymer takes a partially crystalline form like what we have seen here, or whether it takes an amorphous form as shown here. So, for that let us start looking at this concept of tacticity. What tacticity means is, it talks about the arrangement of atoms in this monomer. So, we will start with again polyethylene, the linear polymer chain where it has a carbon backbone, but in addition to that we also have these hydrogen atoms. So, as you can see, like let us say this is one monomer. we have these 4 hydrogen atoms, 2 at the top and 2 at the bottom, and this is the chemical structure. But now let us look at other polymers. So, we will look at polypropylene and polyvinyl chloride. So, how are they different from polyethylene? The only difference is this hydrogen atom is replaced by CH3 in terms of for polypropylene and with chlorine for polyvinyl chloride. So, what is happening is we have this additional subgroup or a radical which is coming into the polymer chain. So, now let us look at, once we have this radical, how does the polymer chain change? So, it can have many possibilities. We will look at 3 of those possibilities. First, let us start with isotactic. So, here R is the radical we are talking about, which could be either CH3 or chlorine, depending on the kind of polymer we are discussing about. So, here in this particular situation we have said all radicals are sitting on the upper side of the carbon backbone. Okay. This is one of the possibilities. Not all polymers do that, but in certain circumstances or the way we process these polymers, this is possible. Another possibility is we have these radicals in a sinusoidal fashion, which we now call it as syndiotactic, meaning, so this is the radical now at the bottom and to the top, and alternatively it is going from bottom to top. Isotactic is when all the radicals are on one side of the carbon backbone, and syndiotactic is when alternatingly they are in a very systematic format, once to the bottom and once to the top of this carbon backbone. And the other extreme is atactic, means there is no order. This radical can take either below or above at any positions in this polymer chain. So, now that we have seen there are many ways this radical can take positions, how does this affect the polymer packing? That is what we are interested in. So, now the question to be asked is, which of these you think will form a crystalline? So, in previous slide we mentioned crystalline is when these long chains fold against each other and then they form a very compact block. So, which of these possibilities can do like that? The answer is the first 3, linear, isotactic and syndiotactic. They can be stacked side by side to form crystals or crystalline structures. And what is the reason for that? Because let us say if you have 2 linear chains, they can be packed very compactly, because for example, these hydrogens can fit into these gaps. So, if you are talking about another chain, so maybe these there are 2 hydrogen atoms which can fit into these gaps, and therefore, they can come very close to each other and form these linear polymers, or they can form these crystalline forms. The same thing with isotactic. Now that all of these radicals are on one side, these radicals can fit in these places. So, these are the radicals from the second polymer chain which can fit into the spaces available here. The same with syndiotactic, because alternatively this radical can fit in here where there are spaces, and of course here in the top. So, for these reasons all of these, the linear, isotactic and the syndiotactic, they can form these crystalline structures. But what about these atactic? Now that these radicals are very randomly spaced, it is very hard when 2 polymer chains come together, they can really sit next to each other in a very compact fashion, because they do not fit into these gaps. For that reason, atacticity leads to non-crystallinity. What do we mean by non-crystallinity? We mean that it is amorphous. So, what we have seen is how the chemical structure can lead to tacticity, either isotactic, syndiotactic or atactic, and this how will it affect the whether it takes a crystalline structure or an amorphous structure. We know once a particular polymer takes a crystalline or amorphous structure, their mechanical behavior is very different. So, we said when these molecular chains come together and pack, they either take these crystalline polymer or an amorphous polymer. When I mean crystalline polymer, we are talking about semi-crystalline or partially crystalline. But now let us look at under what conditions we have these crystalline polymers. First, as we already discussed in previous slide, isotactic and syndiotactic will assist the formation of crystallinity. Okay. Let us look at some examples. To start with polyethylene, I think in one of the earlier video I mentioned what are LDPE and HDPE. LDPE stands for low density polyethylene and HDPE is high density polyethylene. So, we say the low density polyethylene has 50% crystalline form and the high density polyethylene has about 80% crystalline, and usually 80% is the maximum crystallinity we can expect in polymers. Maybe let me also explain why do we have this low density polyethylene and high density polyethylene. The differences are by the way these polymers are processed. So, in low density polyethylene usually the process is very rude or harsh, which means in this process what happens is one of those hydrogen atoms can be plucked out and maybe on that another chain can be attached, which leads to branching. So, I am talking about because of the process parameters, one of the hydrogen being removed and then there is a chain coming there being attached, which leads to branching. As we know, once we have branching, the possibility of them coming together is less. That is why only partially it can crystallize and the rest goes into amorphous. But in HDPE, we can choose some precision manufacturing processes where the polyethylene is less disturbed. When it is less disturbed, it is because of its innate chemical structure, there is a chance for more and more crystallinity, and that is why we get 80% crystallinity with high density polyethylene. Now, moving into amorphous polymers. When do we have amorphous polymers? As we already mentioned, atacity will lead to non-crystallinity or the amorphous polymers. But in addition to that, even branching, as we just discussed with LDPE, let us say branching as you already have shown. So, this is like a branch of a polymer chain, but if you have more and more polymer chains with multiple branches, then there is a chance that they cannot crystallize and then end up as amorphous polymers. Same thing with cross linking. Cross linking is another way of branch linking, but the only difference is here we are using the polyfunctionalities, which means we have a neat network of polymer chains where here we have these cross links. So, when we have these cross links, of course, it cannot be coming together very neatly because these cross links do not let them come to a very compact or a very preferred or an equilibrium position. So, but now let us look at some of the examples of amorphous polymer. An example we will talk about is PMMA, which is a hard plastic, or the commercial name is a plexiglass. The reason why they call it plexiglass is it is used to replace glass because it is transparent and strong. So, most of these plastic windows are made with PMMA, and there are other polymers like this, like the polystyrene and other examples. So, but essentially to see why specifically PMMA ends up as a amorphous polymer is, now you see there are two subgroups in this polymer chemistry. So, because of these two subgroups, now it becomes even more difficult for these two chains to come and pack in a compact fashion, and for that reason they end up as amorphous polymers. So, again like multiple subgroups is another reason why a polymer chooses to end up as an amorphous polymer. So, now let us summarize what we have discussed in this video. We said we discuss the length of a polymer using this concept of degree of polymerization. We also mentioned how we look at the molecular weight of these polymers. We simply multiply degree of polymerization times the molecular weight of the monomer. And we also mentioned that more important is to look at the average degree of polymerization, because not all polymer chains are of equal length. There is a range in this variation in this dP in a single polymer. And we also have showed that this degree of polymerization plays a big role in defining the properties of these polymers. So, meaning that if the polymer chains are long, usually the strength is high, viscosity is high, and the softening temperatures are high. We also looked into the molecular packing, saying that either the polymers can go to a crystalline form or an amorphous form, but usually there is no like a perfect crystalline polymer. Usually it is a semi-crystalline polymer, meaning it has pockets of crystalline as well as amorphous regions. And one aspect of the polymers which decides whether it takes a crystalline form or an amorphous form is the tacticity, which means how the radicals are placed along the polymer chain. So, we discussed about isotactic, syndiotactic and atactic, and said the first three will prefer to go to a crystalline form, but whereas the atactic prefers for the amorphous form of polymers. And lastly, through examples we have seen for a crystalline polymer with polyethylene how it forms crystalline. We said like for the low density polyethylene usually the crystallinity is around 50%, but whereas for the high density polyethylene, that is when we get a high fraction of crystallinity, but that too is limited to 80%. But in the case of amorphous polymers, we showed this example of PMMA or the plexiglass and said because of it having two subgroups or multiple subgroups, it is even more harder to form a crystalline. So, it ends up as a amorphous polymer. So, with this we conclude this video. In the next video we will discuss about a very important aspect of polymers, which is the glass transition temperature. See you then. Bye.